Hello, welcome to this lesson on wave speed. The question of the day: describe how electrons emit energy. You learned back in the very first lesson of this unit about different types of waves, and there are plenty of types of waves, and they carry different amounts of energy. Sometimes they're carrying matter, like think of an ocean wave, right? Then we have light, which moves at the speed of light. So these waves are going to be carrying different amounts of energy, and with that, they are going to be moving at different speeds. So when we talk about waves, a lot of the time, because they're all moving at different speeds, we are going to try to categorize them because waves is just a very big category. We oftentimes are going to group them based on how much energy they're moving or the type of energy that they're moving, and sometimes even the speed at which they move. This unit is largely on light, so this information is really just to give like a frame of reference. The speed of sound is 343 meters per second, and sound is going to require a medium, meaning it needs something to travel through. A lot of the time, that's just air molecules, but sometimes it's solids. It can also be water. You can hear muffled sounds underwater. Speed of light, on the other hand, is the fastest speed that we know to exist. We don't know of anything as of right now that moves faster than the speed of light, and it appears that this is a cap on how quickly matter or energy can move, and that is 3 times 10 to the 8th meters per second, which is 300 million meters per second. That is wicked fast. And then if we wanted to measure that in nanometers, our exponent now is times 10 to the 17th. And that's just because nanometers are crazy small compared to a meter. Now, light does not require a medium. So again, it doesn't need anything to travel through. Light travels through the empty vacuum of space. It does not need air molecules. It does not need dust particles. It does not need a solid. Doesn't need any of that. Light can travel through completely empty space. Does not require a medium. Frequency is the number of waves that pass a particular point in just 1 second. So we're looking at 1 second in time, and then how many waves go through. And we're going to measure that in waves per second, but most often we're going to measure that in hertz, Hertz, and we'll abbreviate that capital HZ. So if we're looking at this picture of a waveform, which is just a picture of a wave, that's what a waveform is. And the question is, if this takes place over 1 second, what is the frequency? So here we would look at how many waves pass in this length of time of 1 second. And a wave, remember, is from crest to crest or trough to trough or from center to center. But if you're going from center to center, you have to include a trough and a crest in that so that your entire wave is sort of S-shaped. It goes either up and then down or down and then up. You have to include both a crest and a trough in the wavelength. So it's really, the question here is how many wavelengths are in this picture that represents 1 second. So starting at the very, very end on the left side of this wave, we're starting in the center and we drop a trough and a crest and then back to the center. That's one. Trough, crest, back to center. Boom. Trough, crest, back to center, trough, crest, back to center. So this would be 4 waves in 1 second, meaning that the frequency here would be 4 hertz. 4 waves pass in this 1 second. The formula for frequency, if we needed to calculate it, would be taking the speed of the wave, which is meters per second of velocity, and we are going to divide that by its wavelength. So in that case, what's going to happen is when you derive the equation, if you were interested in that, it would be meters per second divided by the wavelength, which should be in meters. And then this is going to come out to a number of waves per second, which is going to be hertz. So this works if your velocity and your wavelength are representing the same length type measurement. So if your velocity is given in meters per second, 3 times 10 to the 8th meters per second, then your wavelength must also be measured in meters. You can calculate a frequency using 3 times 10 to the 17th nanometers per second, but then your wavelength must also be recorded in nanometers. So you can plug in a velocity and a wavelength here. It's just that the length portion of the measurement must be the same. Otherwise, you'll have to convert one so that they match. Okay, and your frequencies for the electromagnetic spectrum is going to be typically something like times 10 to the 14th, times 10 to the 15th, something in that range is going to be a comfortable frequency for those waves. Because remember, the electromagnetic waves, even if we're just talking about visible light, the wavelength of visible light, let's just say we're talking about 500 nanometers. That's maybe yellow. Maybe don't quote me on that. So if we're looking at 500 nanometers right here, then this is incredibly tiny. So you should be able to get a heck of a lot of waves passing a point per second. So your frequency is typically going to be something times 10 to the low teens is what we're looking at for a healthy exponent there in the electromagnetic spectrum. Now, if we are talking about radio waves, which remember can be kilometers long, your frequency is going to be a lot smaller, like maybe 10 to the 8th in hertz. And that's just because it takes more time for those crazy long wavelengths to pass. If we're talking gamma rays that have a super, super, super short wavelength, billions of these waves can pass per second. So you will have even more than billions. You would have a higher frequency in that case. So your exponent on the frequency would be very, very high. But for chemistry, for the most part, we're talking visible light, and visible light, infrared, UV, they're going to come in at the low teens on your exponents. Period is not something we often touch on in chemistry. It's a little bit more of a physics term, but just in case your teacher wanted you to learn this, it's here. The period is sort of the opposite of frequency. It is the amount of time it takes for one wavelength to get through. Now, it's usually, for chemistry at least, an infinitesimally small amount of time because the frequencies, the number of waves that pass per second, is times 10 to the 14th. So we are talking about a period that is crazy tiny because that was a billion waves right there. It's super, super small. So we don't talk about this super often, but period is represented by a capital T, and it's just the inverse of your frequency calculation. That is your wavelength divided by the velocity. Let's say you have the wavelength of a wave and you have its frequency. You know how many waves are passing per second. In that case, you can calculate the velocity. And that would be seen as V equals lambda F. Remember, lambda is the Greek symbol that represents wavelength. Now, again, if your wavelength that goes into this is in meters, then your velocity is going to come out in meters per second. If the wavelength that goes into this is nanometers, then your velocity is going to come out in nanometers per second. So just be mindful of those units. Remember, metric conversions, you just move the decimal a few times. I am a very big fan of watching for those nanometers because if you can get a speed in nanometers, I'll show you in this next example, then your wavelength coming out in nanometers just is functionally better. So let's take a look at this. We have a question. It says blue light has a wavelength of 400 nanometers. Does it? Yes, it does. Okay. I'm thinking it's reversed. What is the frequency of this wave? So because this wavelength was given in nanometers, I want my velocity to get plugged into this equation in nanometers, simply because I don't want to do a unit conversion. I just don't. So I'm going to use that times 10 to the 17th nanometers per second as my speed of light. Okay. So we're plugging that in on the top for V. Lambda is the wavelength, 400 nanometers. Just drop that in. And then we plug this into the calculator. Now, what's important here is to remember that 3 times 10 to the 17th must get wrapped in parentheses. Otherwise, this gets a little funky. So on your calculator, you turn it on, parentheses, 3E17, close up those parentheses, divide it by 400, and then we're getting 7.5 times 10 to the 14th. Because we're solving for a frequency, our unit is hertz. Like I said, we're looking in the low teens for our frequencies when we're talking visible light, ultraviolet, and infrared. And those are going to be like healthy numbers. Now, we learned earlier that the speed of light is sometimes represented by the lowercase letter c, like E equals mc squared. So when you see this equation, F equals V divided by lambda, you may see in your teacher's worksheets, in notes, in your textbook, you may see V for velocity represented by lowercase c. It's just a little bit more specific. That's all. Frequency equals V divided by lambda is true regardless of the type of wave. So if it's a sound wave, this is true. If it's a seismic wave, this is true. If it is a wave of water at the beach, it's true. If you drop in C, the letter C, instead of V, it just means you're talking specifically about the speed of light, but it still means speed. Okay, so don't get stressed out about seeing C in place of V. It's all the same thing. Now, looking here at wave speed, if we have each of these waveforms representing 1 second, which of these has a higher frequency? As in, which has more waves per second? I hope that you said wave B because that's the correct answer. Wave B has more waves per second. Mathematically, it's because it has a shorter wavelength and more waves are able to pass per second. And that's it. That's wave speed. If you have any questions, leave them in the comment section below the video. Subscribe so you don't miss the next one. That's going to get a little bit more interesting. We're going to do wave energy in the next video. And I think that's everything. So I'll see you in the next lesson. Bye.